Hello, everyone. My name is Zack Williams, and today I'm going to do my work in progress 2 on my project for the NBA MVP and using machine learning to predict future MVPs. Um, so to dive right in, we're going to talk about a little bit of recap, my motivation for the project and my objective. I'm going to try to cruise through those as fast as I can to get to the meat of this, which is the progress since the last work in progress I did. Um, any data and modeling updates I have, any mathematical and analytical descriptions that I have, um, current analysis, and changes to the analytical timeline that might have happened. Um, so to dive right into motivation, I like to call it the why. I like using why as sort of a launch pad for any sort of question that I pose. Um, so reason number one is that I'm obsessed with basketball. It's my favorite sport. I love studying it. I love looking and researching it. I love playing it. I love observing statistics for it and gaining any sort of insight into the game itself. Um, and so that's reason number one. Reason number two is that I wanted to create a project that was informative and impactful now, but can grow over time through integration of new basketball statistics that appear. I'm going to break this into two parts really quick. Informative and impactful now means I want this project to matter in the present. So in its current state, by the end of the project, I want it to have impact. But I also wanted a project that could grow into something a lot larger. There's a lot more things that I can analyze when it comes to the NBA MVP that I just don't have time to do in the 8 weeks. And so being able to take more time, develop it into an ongoing analysis throughout the season, integrate new and different statistics that might be helpful for predicting the MVP, so on and so forth. So that's why I chose this project, my why for this project. My objective, there's three. One is I wanted to figure out what statistics were best at predicting the NBA MVP. So things like points per game, shooting percentage, usage percentage, all those to figure out which ones were best at predicting who will win the MVP. You can sort of do this just by looking at the statistics, but we wanted to use modeling to sort of figure out the best way of doing it and what metrics are best for predicting. The second objective is to take those findings from the prediction models and then compare it to different sports betting markets like DraftKings or FanDuel or BetMGM and see what the best bang for your buck could be. So we could look at a player's chalk who's favorited to win the MVP, but may have low odds in our model. But then we have a player with better odds who's more likely to win the MVP based on the model. We're looking for those discrepancies to see if there is any and see if we can win a little bit of money on it. And then third and finally, who will win the MVP in 2024? We won't actually be able to predict the 2024 MVP just because we don't obviously have statistics. The season doesn't start until October 24th. But the results will show predictions for the 2022-2023 season, along with every other season before that, to basically showcase how well the models are performing based on actual results, and then take that information and apply it to 2024 throughout the year. So those are the three objectives, and we can move on to some of the new stuff. So progress since the last work in progress. One was data collection. So I was finally successfully able to take all the data, which was roughly about 30 Excel documents, and combine it into one big data set. The 30 different Excel documents are like points per game for every year, advanced statistics for every year, a statistic called Raptor for every year, and then like team standing and stuff like that. And then that had to be integrated all into one big data set, which it was. And I'll talk about that data set a little bit later. Some initial analysis I did was taking this data, trimmed it down, and then created a data set that was much more manageable for the regressors to run. And then speaking of regressors, I started doing regression modeling on the data. So basically I have it running against the entire data set, got predictions for all that, and I'll go into the metrics and what regressors I used later on in the presentation. So that's everything I've done in the past couple of weeks since the last work in progress. And I'll go into a lot more detail on each one of these steps throughout the presentation. So a little bit about the data and modeling that I did. On the left, you see the full data set. So every player from every year since the 2013-2014 season. And as you can see, a statistic called Raptors integrated in there. You have advanced statistics in here, basic statistics, which are just per game statistics. And you can see that it's a pretty sizable data set. So 63 different features, over 5,200 rows of players, player data, all that stuff. And our reduced data set, and I'll get into how I reduce the data set in the next slide, but a reduced data set is much smaller, much more manageable for the regressors to use, and cuts out some of the features that are unnecessary and won't be helpful for predicting the MVP, such like player name and player position and stuff like that. And then statistics that will overfit the model because they're really close, such as like ranking in the MVP standing and stuff like that. So those are two major data sets. We obviously won't use the full data set for much of anything for regression, but it's a good resource to have just in the back pocket for later use. And then our reduced data set is what we're going to run against the regression models. So a little bit more about the data and modeling itself. I like to call this the checklist to becoming an MVP. This is the minimum statistics that an MVP has to have in order to win an MVP. And this is how we got our reduced data set in the last slide. So we essentially filtered the data to only players who have played over 48 games, scored more than 13.5 points per game in a season, averaged more than 30 points per game in a season, 30 minutes per game in a season, excuse me. Have an overall team standing of over 16. There's 30 teams in the NBA, so we're talking about the top half of the league. They have to average more than 1 assist per game in a season, and then they have to average more than 3 total rebounds per game in a season. 7 is have a field goal percentage of over 37% per game in a season. 8th is attempt more than 10 shots per game in a season. And then 9th is, it's a typo, but have a player efficiency rating of over 18 in a game. These 9 parameters were pulled from a website called StatMuse, which has historical data dating back to the beginning of the NBA. And you can basically find rankings for any statistic that you want. So that's where I found these minimums. I basically said, okay, what is the lowest points per game average that a player had in a MVP season? And it came back 13.5 points per game, that sort of stuff. So that's how we got our minimums. That's how we reduced our data set to 227 different players in different seasons and stuff like that. And so then we moved to the regressors we're running. We took that reduced data set, ran it against 4 different regressors, SVR, support vector regression, a random forest regressor, gradient boosting regressor, and our K nearest neighbor regressor. And you'll see we have our squared values for all those and mean sum error for all those values, or for all those regressors. And so I'll go into more detail about what those regressors do, what these scores mean, so on and so forth. But broad overview is a higher R squared is better and a lower mean sum error is better. So you can kind of see that the random forest measured against the entire data set works best. K-nearest neighbor is definitely the worst performing one. And then SVR and gradient boosting are sort of in between. One last note about the data set is that it has a lot of null values. That's because when we took the data set from Excel and brought it into our notebook, the zeros were replaced with null values. And so basically looking through the data set, I concluded there was two different ways to do this. Either remove the null values altogether. And the reason I did that for some instances was that there was another stipulation that wasn't being used in the filtering in Python. That was a player couldn't play for more than one team in a season. And so if a player showed up twice in one season, that player was just removed from the data set. And then the second option was replacing the null values with 0. And so going into the data set saying, okay, these players have a null value, but it's because they didn't attempt a 3-pointer or something like that. So those values were replaced with 0 because it's just 0 out of 0, 0 over 0 as the measurement. So it's a little bit about how my data set looks, exactly some of the modeling that we did for it, the parameters that we chose to reduce our data set, and then how we dealt with null values. So we can dive right into some mathematical and analytical descriptions. So as I talked about earlier, the regression models that we're going to run are going to be support vector machines, specifically the regressor, a random forest regressor, a gradient boosting regressor, and a k-nearest neighbor regressor. I am not sold on using all 4 of them. I think k-nearest neighbor is probably the least informative, and I think removing it doesn't hurt analysis later on, and it doesn't add enough to keep it in. So I think I'm going to reduce the number of regressors. But for now, it's in there, and so we're going to talk about it. Evaluation metrics are going to be R squared and mean sum error, as I talked about earlier. And then I'm sorry, it's mean squared error, not mean sum error. I apologize. And then I'm going to talk through a little bit about what the charts are going to look like, comparative and descriptive charts that we're going to use to sort of look at the data. So to go into a little bit more detail about each of them. So the regressors we're going to use, I've said them a couple times now, but to elaborate a little bit more about each one, what each one does, excuse me. The SVR supports linear and nonlinear regression, and then it is trying to fit as many instances as it can between 2 fit lines while limiting the margin violations. Basically what that means is that there's like a line of best fit, there's data on a scatter plot, and we're trying to get the width of the 2 lines for measuring as small as possible with as little margin violations as possible. So as little points outside of the margins as possible. Random forest is something that fits a number of classifying decision trees on various subsamples of the data set and uses the averaging to improve the predictive accuracy and control over fitting. As I mentioned earlier, there were some statistics that would have overfit the model just because they were drawn essentially from our dependent variable. So basically our dependent variable is MVP share, which is something I forgot to mention earlier. But MVP share is essentially the total number of points you receive from voters for the MVP divided by the total points you could realistically get from voters. It's usually in the thousands. So like a first place vote is worth a certain amount of points, second place vote is worth a certain amount of points, so on and so forth. And then so we can move on to gradient boosting, which is something new that I wanted to experiment with this project. And it's an estimator that builds an additive model in a forward stage-wise fashion. And it allows for the optimization of arbitrary differentiable loss functions. Excuse me. As I said, it's a new one. And so I don't know much about it, and I'm really excited to learn more and understand it and apply it to these problems. And then K nearest neighbor regressors is just a regressor that targets the prediction through local interpolation of the targets associated with the nearest neighbors in the training set. What data clusters together, essentially. And so to evaluate each of these regressors, we are going to use R squared and mean squared error. Both great measurements for evaluating regression models. R squared is measured by taking 1 minus the sum of squares of residuals divided by the total sum of squares. It will result in a higher number for better performance, as we talked about earlier when we were talking about the results I've found so far. And then mean squared error is the sum of squares error divided by the error degrees of freedom. Something we learned in our statistics course about a year ago. And so those are going to be our evaluators for the regression models. And then to talk a little bit about visuals, which we haven't developed yet. We haven't gotten that far, but we are going to use Tableau to do it. Our main plot is going to be a scatter plot, which has probably a x-axis of probably performance for the model and a y-axis of the odds. And basically we're going to plot it against it. We're going to plot probably the top 5 players in the based on the model in there, maybe more, maybe less. We'll see how the data plays out, but that's going to be our main visual. And then a plot that measures the attribute importance for the model. I haven't figured out what plot that's going to be yet, but we want to know what attributes are affecting the MVP most. And so that's something we're going to develop later on. And so we can move right along to any current analysis I've done so far. So a little bit more than last time. We reduced the data set, obviously, as I talked about, for faster run times for the models and better understanding of each variable. And then we're almost through solving how to run the prediction through each year versus actual results that year. What that means is we are trying to isolate the 2023 data and then run that data against the regression models. And so that way we can find who's going to have the highest odds for the MVP based on the model. So what's next? We're going to use model predict the 2022, 2023 MVP using historical data. As I mentioned, we don't have statistics for the 2023, 2024 season yet. So we're going to predict 2022, 2023 to test the model along with other years as well. And then we're going to take the findings and present all of that through different visualizations, as I talked about. And through those visualizations, compare and contrast betting markets to the findings of the regression models. I'm really super excited for some of these results. I can't wait to get them and start analyzing how betting markets are making their moves. Is it how much of it's based on media attention, how much of it's based on what their models are saying, who's going to win the MVP, so on and so forth. So I'm really excited about what's coming next. And then changes to the analytical timeline. So if you've seen my first work in progress, this is very similar to my original timeline. but you can see that I crossed out some stuff. So obviously we've gone through 5 weeks of doing it. We've got through idea development and data collection. And so collected all my data in one data set, developed the idea pretty early on. I've been thinking about this project for a while, and so I was excited I was able to finally do it. The week 3 was data cleaning and preliminary observations. So that was reducing the data set based on the minimum parameters, and then looking at the data and seeing exactly what it's supposed to show us, essentially. And then these past 2 weeks, I've just been working on doing the data modeling and analysis. So running the data set through the regressors, trying to figure out ways to run each year through it as well. And so this upcoming week, we're hoping to get that finished. And then week 7 is just probably all about taking that data, running to Tableau and plotting it and making it presentable for week 8 for our final presentation. And so that's my project. Really excited about the findings that I'm hopefully going to find this week, and be able to present to you guys by the end of October. I appreciate everyone's insight on this. Any feedback is greatly appreciated, and I will talk to everyone later.